We're going to talk about atomic structure, and symbolism, which is going to lead us into a discussion about, obviously, about the periodic table. We'll introduce a little bit of that today. And based on that, we're also going to talk about formulas and naming. All right, so we'll start out talking about atomic theory and some early atomic theory, somewhere around 5th century BC. That's when Greek philosophers like Aristotle and other philosophers of the day came up with the idea about like matter and what matter is composed of. You know, Aristotle, his idea was that matter was composed of, all matter was either earth, wind, fire, or water, right? But eventually, the term atomos came out of that, which literally means indivisible, right? So the Greek hypothesis, because it's all hypothetical, they had no way to study this, was that all matter consisted of small particles, right? All matter consisted of small particles, and those particles were capable of joining together. I'm going to say bonding. They didn't say bonding because that wasn't a term that was used back then, but I'm going to say it. So the particles that are in matter have the capability to form bonds between each other. Right. So again, all of this is hypothetical. There was no way to study atoms. There was no way to study the composition of an atom. There was no way to study um, these particles during this time. And so it was, centuries later when John Dalton developed the atomic theory. So that's what we're going to talk about now. So Dalton's atomic theory. All right. And then keep in mind, when we say that something is a theory, what do we mean? What does that word mean to you? Now that we've studied that in the first chapter, what does that word mean to you?
Like a guess?
That would be a hypothesis. A theory is a body of knowledge, a huge, vast body of knowledge that's used to explain an observation. All right. So Dalton, through experimentation, based on the hypotheses that were out at the time about atoms and matter and how matter is composed, he developed a theory to explain the behavior of matter. So one of the things that, and it has 5 parts to it. Right. One is this, that matter is composed of atoms, right? It sounds repetitive, but you have to be able, he was actually able to show that atoms existed and also that atoms had components. So let me fix that. Right, matter is composed of atoms. And you know that an atom is the smallest part of an element. And the atoms that matter is composed of, they can participate or undergo chemical changes. Right? So matter is made up of atoms, and those atoms can undergo chemical changes. All right. So atomic theory, again, is used to explain the behavior of matter. All right. Matter is also exclusively composed of atoms, and then the elements where the atoms come from are exclusively composed of specific types of atoms. So an element, if you think about sodium, sodium is an element, and sodium is composed of, the element sodium is composed of only sodium atoms, no other atoms, right? Same thing with chlorine. Chlorine is an element, but when we think about the element chlorine, it is made up of only chlorine atoms, right? So the elements are exclusively composed of one type of atom. That's the second part of the theory. One type of atom, right? Only one type of atom. And because of that, uh, the every element has its own specific properties, right? Because it's only composed of one type of atom, that means that elements have their own properties, exclusive to that element and different from other elements, all right? The third part of the theory says that elements are different because of the atoms that make them up. So elements are different because of the atoms that make them up. And then the fourth part of the theory says that when you start adding atoms together, atoms of different elements together to make compounds, these atoms combine to make compounds in.
I'm sorry, can you slide back up to 2?
Mm-hmm.
Thank you.
Yeah, you good. All right, so when atoms of specific elements start to come together and make compounds, then those compounds exist in with ratios between the atoms of small whole numbers, right? So compounds, we're going to talk a lot about that in a second. So ratios of, let me zoom in so I can. Of small whole numbers, right? Let me give you an example here. So an example of a compound, we've seen this before already, but I'm just going to give you another example. So calcium nitrate. All right, calcium here. Is the element, right? So you have an atom of the element calcium combining with what we call nitrate ion, right? Which we also call a polyatomic. Just write this term down. This is a very important term. We're going to talk more about it later. But this is a polyatomic ion. That's what nitrate is. And I'm going to show you how this comes together, even though when we talk about making compounds and combining atoms, it'll be later. But I'm going to show you now how we make calcium nitrate. Not make it, but how we develop the formula for it. All right. So you got an atom of calcium.
Which word do we need to write down?
Polyatomic. Well, all of it really, but the polyatomic ion is in reference to the nitrate. And I'm gonna show you why we call it a polyatomic and why we call
Excuse
it
me,
an
can
ion.
you go back to number 3? Thank you.
Mhm. So number 3 says elements are different because of the atoms that make them up. Number 4 says compounds exist when atoms combine in ratios of small whole numbers. All right, are we good now?
Yes, thank you.
Okay. So when we think about calcium nitrate, can somebody look at the periodic table and tell me what column calcium is in? Start at the left where hydrogen is and work your way to the right. Tell me what column calcium is in. Anybody got it yet?
The second,
It's in group 2, isn't it?
yes.
So it's a group 2 element. And then the nitrate, we'll talk more about that later, but it's composed of, in this particular case, 1 nitrogen atom and then 3 oxygen atoms bonded together in a specific way, right? But it's charged, and I'll show you. So group calcium is group 2, so that means that any time you have calcium, it's going to have a charge of +2, right? Anytime you have calcium, it's got a +2 charge. And then when you take the nitrate, this whole thing together as a group has a charge of -1. Right. So when we combine these to make a compound of calcium nitrate, I'll show you what happens. So we take, and I'm going to put a plus here, even though this is really like there will have to be something else bonded to calcium and something else bonded to the nitrate, but we're not going to worry about that at this point. Right. We use, in this particular case, because if you notice up here, there's a 2 here. That 2 is there for a reason. So we use what's called the crisscross method. How many of you have heard of that in when you took chemistry before? All right, so we're going to take the 2 here and put it here. We're going to take the 1 here. We're not worried about the charge and put it here. So when those 2 combine, we have Ca and then NO3, 2, right? The 2 goes outside the parentheses, and then the 1 is understood to be here, but we don't have to show it. Right. So how many what's the ratio in this particular case of calcium to nitrogen? Anybody? How many calciums are present? How many nitrogens are present?
There's 2 calcium and is it 5 nitrogen? 3.
Okay.
No, it's 1 calcium. It's 1 calcium.
1 calcium. And then there are, because of this 2 right here, 2 nitrogens. So the ratio is 1 to 2. I'm just making the point about that 4th rule about when you combine atoms to make compounds, there are specific small number ratios that these atoms combine in. What about nitrogen to oxygen? What's the ratio there?
2 to 5.
All right. So 2 nitrogens, 2, actually it is, you have to multiply that right there. So it's 6. So 2 to 6. And don't worry about if it's not clicking, because we're going to do a lot of this. I'm just using this to make a point. That when you make compounds, they come together and they have specific ratios of atoms in those compounds. All right. So the ratio of calcium to nitrogen is 1 to 2, nitrogen to oxygen 2 to 6, and then of course calcium to oxygen will be what? How many calciums do I have?
1,
1. And how many oxygens do I have?
6,
6. That's not going to change, right? That's one of the things that we're going to talk about in a second, is this law of constant proportions, where no matter where you get the calcium nitrate from, the ratios of the atoms will always be the same. All right. So that's the fourth part of the theory of Dalton's atomic theory, that compounds exist when atoms combine in ratios of small whole numbers. All right. Hopefully that wasn't too convoluted, but we're going to talk a lot more about this. And then the final part of this theory, or the final point in the theory, is so we know that these are small whole number compounds. When the final point is very important. When reactions happen, atoms do not get destroyed. They don't get created. They only rearrange. So anytime you have a chemical change, right, the atoms get rearranged. You can't destroy an atom. You can't create an atom out of thin air. You can only rearrange them and how they interact with one another. So those 5 points make up Dalton's theory or Dalton's atomic theory. Matter is composed of atoms. Elements are made up of one type of atom. All elements are different from one another because they're all made up of a different type of atom. And then when you make compounds, the pieces that make up the compound are present in small whole number ratios. And then if anything that undergoes a chemical change will by default have its atoms rearranged, right? So you get something different. All right. So all of this theoretical information helps us to explain like how atoms behave, how reactions happen. And then when we look at especially when we start talking about compounds and we start talking about chemical changes, there are specific rules that compounds follow, right? And one of the scientists who studied like compounds and how they are made and how the composition doesn't change from place to place, no matter where you get the compound from or from source to source, the composition of the atomic composition does not change. And one of the scientists who studied this is Joseph Proust. He was a French, I think he was a French physicist. No, he was a French chemist, I'm sorry. All right, so Proust developed what we call the law of constant proportions. Law of constant proportions. What that law says is this: if you have a sample of a pure compound, every sample of that pure compound, no matter where you get it from, will have elements present in a specific ratio, right, by mass, right? So the proportions of the atoms that make up that compound are going to be present in the same proportion, regardless of the source of the compound or the origin of the compound. They'll be present in the same proportion by mass, right? So let me write that down. So all samples of a pure compound, no matter where you get it from, all samples means I can dig it in my backyard. I can buy it from Aldrich. I can make it in my kitchen, whatever. If it's a pure compound, all the samples are going to contain the same proportion of elements by mass. I'm going to say ratio instead of proportion. Right? So if I take a 10-gram sample of a pure compound, it's going to have a specific ratio no matter where I get it from. If I take a 20-gram sample, of course, if I change the mass, right, the mass, the proportion of the elements is going to change a little, but it's going to be in the same ratio, right? So it'll contain the same ratio, right, of elements. So let's look at an example, right? If I take if I take a water molecule, right? If I take a water molecule, like so. So this is water. What's the ratio of hydrogen to oxygen? How many hydrogens are present?
2.
2 hydrogens.
2 to 1.
Excellent. Great. Excellent. So I have two hydrogens to 1 oxygen. That's not a 10. Let me fix my 1. I had to draw like a kindergarten 1. And I'll put a little X here. That's not the symbol for oxygen, by the way, but it's very difficult to distinguish between a 0 and an O when you're writing with your fingertip. All right, so 1 oxygen and 2 hydrogens. All right, so we have that ratio, and now because of that, we also have a mass ratio that we know for every molecule of water, right? So if I have 2 hydrogens, let's look at this right quick. Let me switch to my screen, and I want to show you something, right? The key to understanding this law of constant proportions is that you need the atomic mass of whatever the element is in order to figure out the mass ratio. All right, come on, computer. All right, so I'm going to send you a link to this, by the way. This is an interactive periodic table. And so when we look at the periodic table, and trust me, we're going to get a lot of run with this periodic table. When you look at hydrogen, which is here, that number right there, 1.008, is that's the atomic mass for hydrogen. So we can say that every hydrogen atom has a mass of 1 atomic mass unit. We're going to talk more about AMUs later. So if I have 2 hydrogens, what would the mass be if I had 2 hydrogens? The mass is not going to change, but what would the mass of 2 hydrogens together be?
.016.
Yeah, 2.016, or we round up, we'll just say 2.0. All right. Now let's look at oxygen. If you go over to the other side of the periodic table, all of this right here in the middle, these are all what we call transition metals, right? And then down here you have another class of metals, lanthanides and actinides. They do really different chemistry from the other transition metals because they have so many other orbitals and electron shells that they do a lot of different chemistry, right? But when we get back over here, right, on the other side of boron and aluminum, these are what we call metalloids. And then on the other side of this, you have carbon, nitrogen, and oxygen, and you can see the mass of the atomic mass of 1 oxygen atom is 16 atomic mass units. All right. So let's go back to and I'm going to send you this because if you click on any element, it'll tell you something about it. So I'm actually going to send this to you so you can save it and use it at your leisure whenever you need a periodic table. All right, so let's go back to the example. All right, so we know the mass of hydrogen is going to be 2 times whatever the atomic mass is, right? So that's 2. And then for oxygen, it's going to be 1 times what? What do we say the atomic mass for oxygen is? All right, it's 16. Right, so the ratio, the mass ratio for this compound, which is water in this case, is going to be 1 gram of hydrogen for every 16 grams of oxygen, right? No, let me take that back. Let me fix that because we said hydrogen was 2. It's 2 grams of hydrogen for every 16 grams of oxygen. Or if we can reduce it down and say 1 gram of hydrogen for every 8 grams oxygen. Are y'all following? Any questions about that? So the point is, I could take water from my toilet. I can take it from a spring or a waterfall or wherever. The law of constant proportion says that no matter where I get the sample of the compound from, the mass ratio is going to be the same no matter what. Right. So for water, the mass ratio is 2 to 16 or 1 to 8. However, if some cases we'll have to reduce it, especially when we're doing the law of multiple proportions, we have to reduce it. But for now, we're gonna hold this. So the law of constant proportions says that all pure water samples, no matter where they come from, will have that same ratio by mass. Right, all water samples. Is that clear? Anybody not following that? Right, but in order to determine the mass ratio, we need the atomic mass. You have to have the atomic mass, right? So you have to know the atomic mass, and we get that from the periodic table. Right. Once you know the atomic mass, you can figure out the ratio. All right. So what Proust did was he was actually studying copper carbonate.
Can you go back up a little bit?
Yeah, no doubt, no doubt. All right. Anybody have any questions? Let me put a divider here. So it was Proust's study of copper carbonate that allowed him to develop this theory. So he took a natural sample. And he took a sample that he made, right? And both samples were 100 grams. That's very important because the proportion or the ratio is always by mass. So both samples were 100 grams. And what he found was that the ratio of copper, the carbon to oxygen was always 51.35%, 9.74%, and 38.91%. Always. Right. And so from those observations, multiple observations of the same outcome allowed the development of this law, the law of constant proportions. All right. Let's look at a couple of examples to kind of bring this home. And then what we'll do is on Monday, we'll move into the law of multiple proportions, but I want to try to drive this home today. So anytime you have this law of constant proportion, you have a problem dealing with that. There's a strategy we can employ, right? First thing is we need to we need to know the atomic masses. Right, you have to have the atomic masses. And then you're also going to need a mass to determine the ratio, right? You're going to have to know how much of the compound you have, or how much of one particular element is present in that compound, in order to determine how much of the other element is present, right? So we also need a mass of one of the components. When we do that, then we'll be able to figure out we can determine the ratio from the atomic mass, and then we can also derive the other element in that compound by simply using a conversion, using the ratio like a conversion factor, right? So let me put that in here. And again, I can't stress it enough. That's why we spent so much time on everything from this point forward is going to have some type of conversion or ratio or something. So it's really, that's an invaluable skill set to have, to be able to apply all of those skills to various problems that require you to convert between, different types of elements. Maybe it's converting between different units, so on and so forth. Right. So let's look at the example. So let's say we have a pure sample of sodium fluoride. You can see that this is a compound, right? There's two atoms of two different elements together, so that makes it a compound. And if we have a pure sample of sodium fluoride, and it contains 35 grams of sodium, right? We can answer the question, how many grams of fluorine are present? Right? We can answer that question. If we know how much sodium we have, and we know the atomic masses, so we can set up a ratio, we can figure out how many grams of fluorine are there as well. All right. So I'm gonna put the link to this in the chat. I need somebody to pull this periodic table up for me. You're gonna be our atomic mass person, wherever you may be. So I'm just, somebody take the initiative on this and pull that periodic table up on your computer or your device. And so you can, so I won't have to keep switching back and forth.
What you need from it?
Okay. Can you look up, so the first part of our strategy is to find the atomic masses, right?
Yes.
So can you look up the atomic mass of sodium, which is Na? It should be in group 1. Is that right? First
Yes.
one. What's the atomic mass? The number underneath it.
23.
23 AMU. All right. And then can you go all the way over to the next to last column and find fluorine? It should be the very top element with a symbol of F.
9.
Is it 9 or 19?
Wait, no, I'm sorry. This periodic table don't have it.
The one I just put the link in the chat for?
Oh, okay. I did. I went Googling for my own.
Oh
I'm
no,
sorry.
you use the one I put in the chat, because I was Googling this morning, and you can ask the class from this morning. We pulled up like 4 different ones, and they were all screwed up. 9 is the atomic number. It's the number of electrons and protons. But
Okay.
19 is the actual atomic mass.
19.
Okay, so 19 AMU. We'll talk about the units later. All right. So we know now that in any sodium fluoride compound, the ratio of sodium to fluorine is going to be 23 to 19. So this is my ratio. 23 sodiums, 19 fluorine. And when I say ratio, now we're talking about, let me add it over here. This is the mass ratio, because we looked up the atomic mass, right? 23 AMUs for sodium, 19 for fluorine. All right. So now let's go back to the question. The question says, if I have a pure sample, that's telling me that I'm going to be applying the law of constant proportion because it's a pure sample. And it says that if I have a pure sample and that sample contains 35 grams of sodium, how many grams of fluorine are present? What can we do with that ratio if we know how much sodium we have? Isn't that ratio nothing more than a conversion factor? Right? Because in that ratio, what we're saying is that 23 grams of sodium is going to be 19 grams of.
Can you stroll up just a little bit while you write? Well, zoom out. Thank you.
Is that right? That ratio is a conversion factor. If I have sodium, but I don't have fluorine, how can I rearrange that ratio to solve for fluorine? If I got 35 grams of 35 grams of sodium, can I just interconvert between fluorine and sodium? Can I do that? Because that's what that ratio is. It's a conversion factor. And it allows me to convert or interconvert between the atoms that make up any compound. As long as I know their atomic masses, that proportion is going to be the same no matter what by mass, right? So anytime I have sodium fluoride, the proportion of sodium to fluorine is always going to be 23 to 19. And whatever mass I have, I can figure out the other mass. So if I know the amount of sodium, I put S. Come on, Russell, tighten up. I can, grams of sodium here is going to cancel, and then that's going to give me a number. Can somebody look that up or type it in to your TI 9000? Anybody got it?
I got 28.9.
28.9. Excellent. That's it. That's it. That's what we're looking for. 28.9 grams of fluorine. So in this sample, a pure sample of sodium fluoride that contains 35 grams of sodium, because of the ratio of fluorine to sodium that we can determine based on their atomic masses, that sample has to have 28.9 grams of fluorine, that 35 gram sample, or that sample, because we don't know how much of it we have, right? But if it contains 35 grams of sodium, based on the law of constant proportions, it's got to have 28.9 grams of fluorine. So the total amount will be what, 63.9? The whole sample itself will weigh 63.9 grams. Is that right? 35 plus 28.9? All right. Any questions about it? We're gonna stop here, and we'll do some more of this on Monday, God willing, and then we'll also jump into the law of multiple proportions, which I'm gonna send you out a couple of videos to check out for that too.
Oh, I
Okay.
have a question.